Good evening, everyone, and welcome to the February meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. We've got a great program for you today. We're going to start with some of our usuals. Dave Chisholm with Ottawa Skies, Al Scott with his 10-minute astronomy news. Janet Tulloch will be giving us a great talk on outstanding standing stones. Then we'll go to the break, after which we'll have Jesse giving us a talk on Oumuamua. Then we'll close off with observations, announcements, and door prizes. So these are our new members over the last month. Welcome. And we've had 16 new members in 2019 thus far. All right, members in the news. So it looks like Michael Wolfson had this article picked up there on the Dominion Observatory. So hopefully they'll get some traction on attempting to preserve that site. All right, and we'll get started with Ottawa Skies. Dave, you're up.
Okay, let's see what's happening in our cloudless skies here in Ottawa. Full moon is on February the 19th. This moon is also known as the full snow moon, just what we need. Or the full hunger moon, as its hunting is difficult at this time of year. This is the second of three supermoons for 2019. The next supermoon is March the 21st. So we have a number of comets this month for you folks to look for. Comet 46P Wyerton and 38P Stefan Oterma. They're very close together in the sky. Maybe you can kill two birds with one stone. We've got Comet C2018 Y1 Iwamoto. This comet could become as bright as magnitude 7 when it swings 0.3 astronomical units from Earth on February the 12th, just 6 days after perihelion. On that date, it will sit in the sickle of Leo with the moon at its first quarter, so it'll be a good opportunity for observing that. For a few evenings around that time, the comet's apparent speed will average 7 degrees to 8 degrees per day. This is an interesting comet to pronounce. Comet 29P Schwarzmann-Walkman hangs in the western Pisces, where it'll be observable through mid-February, and then after conjunction with the sun in mid-March, it returns to the morning sky in late May. It's still moving east in Pisces. The comet is subject to outbursts at any time, which can raise its nominal magnitude of 14-15 to as bright as 10.5. The cause of the outburst may be due to pressurized pockets of carbon monoxide and methane beneath the crust that erupt explosively as cryovolcanoes due to solar heating. If you're interested in sort of keeping a tab on what's happening with the comets, there is a Yahoo group here. I've given Gordon my slides, so you don't have to write this long URL down. When he sends his astronauts out, it will be there. But if you subscribe to that list, you'll be getting emails when interesting things happen with comets. Let's take a look at some of the planets then for the month. Mercury, greatest eastern elongation is on February the 27th. Look for Mercury in the western sky just after sunset. Venus is visible in the early morning. Mars is visible in the first part of the evening. Jupiter is visible just before sunrise. Saturn is visible just before sunrise of the last half of the month. Uranus is visible all night, and Neptune is visible the early part of the evening, first half of the month. And there's our cartoon of the month. Thank you.
All right, thanks, Dave. So up next we have Ottawa news, astronomy news, but I haven't seen Al here today yet. He did send me an email to say he was running a little late. So I guess he's not here yet. Yeah, there's a traffic jam on the 417, as I understand it. So instead, we'll skip Al's segment and go straight to Janet's presentation. And we'll circle back to Al once Janet is done, if he's made it through the traffic jam. Thanks, Janet.
Thank you. So the title of my talk is Outstanding Standing Stones, Neolithic Orkney Winter Solstitial Alignment, and the Cult of Ancestors, Part 1. I think this is the first time that I have presented to you in my capacity as a historian of religions, so I just want to give you a bit of my background. I earned my PhD in religious studies from the University of Ottawa in 2001, where my supervisor was a classical archaeologist specializing in ancient Greek pottery and culture. My own expertise is in the material and visual culture of burial customs in religions of antiquity, specifically ancient Roman religions and early Christianity. Although my expertise does not go as far back as Neolithic religions, I do recognize certain patterns that have resonance with later burial customs of religions from antiquity. In beginning this presentation, I want to say a few words about the framework of religions from antiquity, as this context, I believe, will help us when we go further back to the Neolithic age. Keep it there. So, religions within antiquity, and by that time period I'm talking about 800 BCE to about 200 AD, are what historians call cults. So set aside any contemporary understanding of this term and keep in mind the ancient understanding of the word. Namely, it was the worship of a particular deity or deities with some type of representation of the deity present, such as a carved statue or a three-dimensional image. It could have even been an animal or a reptile, or of interest, rocks, such as meteorites that fell from the sky. Typically, the cult involved animal sacrifice on specific days relating to the deity. Discussions of morality or ethics were the provenance of philosophers, not religions. So very, very different from how we perceive religions today. Excluding ancient Hebrew religions in antiquity did not have scriptures. If it was a mystery religion, for example, like the Eleusinian mysteries that took place near Athens, the lack of any sacred text was intentional. Ancient texts that do survive relate to origin stories of creation, or origin stories of the gods, for example, Hesiod's Theogony, or poetry about heroes and heroines, such as Homer's Iliad and Odyssey, to cite two familiar examples. Other surviving texts relate to rituals or spells, the correct way to perform a ritual. The best example of this is the Egyptian Book of the Dead, or better translated as spells for going forth by day, whereby about 1900 BCE, well-to-do Egyptians could purchase a collection of these spells written in papyrus from scribes and a kind of manual for the afterlife, if you like, to assist the deceased who would be buried with their own personalized book to help them navigate the dangerous place of the underworld in order to reach their happy place in the afterlife. This written evidence is also corroborated by illustrations in the pyramids. Calendars, if they existed, were not secular. Priests controlled the naming of the days and defined which activities were appropriate. As late as 46 BCE, Julius Caesar, whom I'm sure you've all heard of, put a stop to this in Roman religions by wresting control away from the priests by becoming the high priest himself, and hired astronomers from Alexandria to correct the Roman calendar so that it had some semblance to the actual solar year. Later emperors maintained this tradition. In ancestor cults, the spirits of deceased family members are thought to require the assistance and nurturing of their living descendants. In turn, if properly respected, the ancestors would assist their living descendants. The Romans had an extensive ancestor cult, which morphed into a cult of the dead, where great feasts were to be had on specific days. So keeping that framework in mind, let's turn to Neolithic Orkney. The Neolithic period for Orkney is about 1,000 years, roughly, give or take, from 3,500 BCE to 2,500 BCE. And if you don't know where Orkney is, I've set up this map, so most of us probably know where Scotland is, and Orkney is the small set of islands, about 60 islands or so, in between the northern tip of Scotland and Shetland. And here's a close-up of the islands. And the area that I'm mostly going to be talking about today is here. It's called the Heart of Neolithic Orkney, and it was named a World Heritage Site by UNESCO in 1999. So note the list over here on the right. It's a list of Neolithic sites from an article titled Islands of History, the Late Neolithic Timescape of Orkney, that was published in the journal Antiquity in 2017. It excludes North Ronaldsay. And this is interesting because North Ronaldsay boasts both a standing stone with a hole in it, aligned to the midwinter sunset, and a stone cairn at the southwest end of the island. As we can see here. Here is Loch Gretchen, there's the standing stone, and there's the cairn. And on Google Earth, you can see here where I've circled it, the standing stone and the cairn. So there is evidence of Neolithic activity on Orkney, on North Ronaldsay, but it's such a small island, it hasn't really gained a lot of attention. I believe the reason the North Ronaldsay monuments have been overlooked in this particular analysis is because there is no scientific data available to the researchers to process, given so much past attention and even current attention is on, sorry, I'll go back here, is on this area in here, or in here, where you see the cluster of sites. But we will return to this tiny island in the North Sea in a few moments. So, using the first and third of the above methods for dating in Neolithic archaeology, calibrated radiocarbon dating, which most of you are probably familiar with, the loss of carbon-14 in organic matter. The less carbon-14 there is, the older the matter it is. And luminescence dating, which is a little more unfamiliar, but has to do with ionizing radiation from the high-frequency part of the electromagnetic spectrum and its deposits into minerals. These scholars took a sample of about over 700 measurements. 613 were radiocarbon measurements and 79 were luminescent ages from 31 different sites, and they analyzed them, and this was done in 2017, so it's very recent data and analysis for trying to determine a chronology of Neolithic sites within Orkney. Without a sound chronology, we cannot really create an authentic cultural narrative concerning the history of the people who lived there. So based on this article and a couple of others that I researched on Stonehenge, I was able to come up with the following Neolithic chronological model. And as you can see, I added a couple of Neolithic references that you might be more familiar with. to give us a sense of comparison about where Orkney stood during this time period. The Ness of Brogar Orkney, which is now seen fairly clearly as a community gathering and feast site, was not, the excavation for that did not even begin until about 2002. More familiar and excavated earlier in the 1980s would be places like Maze Howe, Orkney, Barnhouse, Orkney, Scarabray, which most of you might be familiar with, and the Stones of Stennis. So to turn to a discussion of the heart of Neolithic Orkney and solstitial alignment, we're going to look at Maze Howe, which is pictured here. It's part of that crowded area I showed you earlier of mainland Neolithic sites. Maze Howe is a chambered tomb which consists of a grass-covered mound about 35 meters in diameter and 7 meters high. It sits on an oval platform enclosed by a wide ditch and outer bank. Including these features, the monument measures about 80 meters north-south by 70 meters east-west. The outer bank dates to the Norse period, though some sample trenches excavated in the 1980s suggest an earlier phase of construction with a low stone wall. Evidence of sockets for large standing stones around the outside of the mound, so in this area, have been found. Carvings on some of the stones inside the chambers, the burial chambers, bear a resemblance to those found at Scarabray and the Ness of Brodgar. The entire passage, or the entrance passage, this area here, is 14.5 meters long and 1.5 meters high, and it's lined with huge slabs, the largest weighing over 30 tons. When the tomb was opened in 1861, the building was empty except for a piece of human skull and some horse bones. However, the Vikings had made an earlier intrusion into this tomb around the 12th century and left one of the largest collections of runes in Britain, as well as carvings of a dragon, a serpent, and a walrus. The solstitial alignment of burial mounds, such as Maze Howe, with its long passageway, lasts for about 3 weeks prior to and after the midwinter sunset. On the day of the actual midwinter solstice, the sun reaches back to the wall of the largest burial chamber, which is here. But up to, before, and after, it slowly creeps across the passageway and partially up the wall until we get this image of a full blast of sunlight against the back wall chamber. The original stone blocking the entrance to the tomb found inside the passageway is trapezoidal in shape. When butted up against the entranceway, it does not completely block the light, regardless of its positioning. So even when the tomb was closed, there still would have been light that entered it. So rather than perceiving this duration of daylight as an error in precise solstice alignment or measurement, I would suggest that such a lengthy period of midwinter light would have had both a practical as well as a metaphysical use, whereby the living could inter the bodies of the recent dead and deposit the bones of ancestors they carried with them. On a metaphysical level, the midwinter lighting of the passageway would have assisted the spirits of the deceased family members to find their way on an afterlife journey, much like the ancient Egyptians, that either began or ended at the tomb on midwinter. This is a shot of the standing stone or the Odin stone from North Ronaldsay, Orkney. The Standstone, or Odenstone in North Ronaldsay, is also aligned to the midwinter solstice sunset, with a similar margin of sunlight passing through it some days before and after the winter solstice. So it's very similar to whatever phenomena is happening at Maze Howe. It's happening here as well. But to my knowledge, neither it nor the cairn on North Ronaldsay has ever been scientifically investigated. Back at Maze Howe, which was thought to have been constructed as early as 3500 BCE, and that is based on very recent analysis of the radiocarbon deposits and as well as those luminescence ages I mentioned. So we're getting closer to more precise dating for this whole area. It's not surprising that archaeologists did not find any remains, neither interred bodies nor artifacts. We know that the tomb has been disturbed many times, most famously in the 12th century by Norsemen who carved about 30 rune inscriptions, mainly in the style of Thorfinn wrote these runes, something similar to Kilroy was here. Some of the inscriptions gave the father's name or a nickname. Others are by women, interestingly enough. And several of these inscriptions are naughty bits about women. This was, of course, long before the #MeToo movement. We can date the runes by a 12th century AD text called the Orkneyinga Saga. It tells the tale of early grave disturbers Earl Rognavold, who was sheltered in this cairn on his way to the Crusades in the Holy Land. Later, in 1153, Earl Harold and his men were caught in a snowstorm on their way to Scotland, and to escape the storm, they broke into the cairn and carved inscriptions on the walls of the inner chamber until the storm passed. There is another passage burial, however. It's a passage burial mound called Midhoe. So you have Maze Hoe and Midhoe. Midhoe is on the island of Rousay, Orkney, is just slightly north of the mainland, which we've been looking at. It's close in size and dating to Maze Howe, and in parts of it, some of the remains were not disturbed. And what archaeologists found here suggests that my supposition about an active cult of ancestors just might be on the right track. Unlike Maze Howe, Midhoe is a stalled type cairn. So, for example, you see a long passageway with regular slabs dividing small little compartments, or what are called stalls, for inhumation interment. Originally, it was an oval mound covered by turf and sediment with about 25 separate compartments. The tomb is 33 meters long, Maze Howe is 35, and 13 meters wide, with a long, narrow central passage of 23 meters, which you can see. When the cairn was excavated in 1923, the archaeologists found the complete remains of 9 people in stalls, arranged on their sides, curled up, facing the central passage, right here. 3 more skulls were set upon a low stone bench on the north side of the chamber. Archaeologists are unsure whether the tomb was ever fully closed. Some theorize that when in use, approximately 3300 to 2700 BCE, the living might have been able to come and go inside the tomb, arranging the bones of their newest ancestors to intentionally face the central passage, while the bones of the older ancestors were gathered into a heap and placed on a shelf, sometimes with their skull sitting on top. The tomb entrance is oriented to the southwest, over here. There's the north directions. But there's never been any mention of either the rising sun or sunset traversing its passageway on solstice days. However, Midhow has a horn-shaped forecourt. In fact, it has two, here and here, whereby if one extends the curvature of these horned passageways, it suggests an original diameter of as much as 70 meters, indicating a space capable of holding hundreds of people for ceremonies. So when viewed together, the monuments of Neolithic Orkney, that is to say Maes Howe, here, the Ness of Brogar, which is actually here, it's not on our map for some strange reason, which is a complex of Neolithic buildings dating somewhere between 3100 BCE up to about 2700 BCE, which I'm going to talk more about next time. Plus, there are a number of smaller chambered funerary sites or cairns around this complex. All of these elements together appear to be the remnants of a late Neolithic shared ancestor cult. Whether the North Ronaldsay stone and cairn were part of this cult remains to be seen. In part 2 of this presentation, which I believe will be in April, I will discuss the nests, the rings, and the smaller burial mounds to show what further evidence reveals about Neolithic religion in Orkney and its relationship to solstitial alignment. Thank you.
Thanks, Janet. Does anyone have any questions or anything? We can take a couple.
I have one question.
Yes?
Was this a natural migration from Orkney down to Stonehenge over the years?
Actually, some scholars are suggesting it was the other way around. Stonehenge is actually younger than Orkney. There have been finds found in the Ness of Brogar which are identical to some of the finds in Stonehenge. But we don't know enough yet about this area to be able to say definitively which way the migration went. But there are some scholars who are suggesting, yes, that Orkney was in fact the place to be in this particular period, and that eventually migration for this type of funerary-related religion swept from Orkney down into southern England. But of course, for the longest period of time, we have seen it the other way around. Okay.
Paul?
Hi, Janet. Sorry, you may have already covered this. I was a bit late coming in. Do we have any handle on who the builders were?
Yeah, there is some suggestion that at the various feast sites, like the Ness of Brogar and Durrington Walls in Stonehenge, that the builders came from different parts of Britain mostly, and some from actually Scotland, to build these monuments. But again, it's work that still needs to be done. I would say probably for Stonehenge we have a better idea of people coming from all over Great Britain, but for this area much less DNA work has been done on the bones that are in the Ness of Brogar area.
Any other questions?
I can answer more at
I think I see one in the back.
Orkney's rather remote, and yet I'm just wondering if there's some trade routes or transportation routes that predate the Vikings that actually populated
Yeah, so far, the DNA evidence, and we're talking roughly 4,000 BCE, is that Orkney and Great Britain and Scandinavia was settled by people who came from Central Europe. There's no question that some sort of exchange practices went on. And at the Ness of Brogar, they've actually found bits of amber, which are not found naturally in this area. So all we can say is that various theories have been given as to what caused the migration. But we do know that by about 2700 BCE, this entire area of Orkney, including Skara Brae, seems to shut up tight. Like the people just leave. They compare it to a kind of Pompeii situation where people seem to have left in droves, but we don't know why.
All right, let's do one last one. Yep.
You talked about three methods of the dating. I guess it would be hard to calibrate the dating method because you'd have to know how old something is. So does it make sense to use the three methods of dating for more accuracy?
Absolutely, and that's what's being done. All three methods are being used, and in fact, when radiocarbon dates were originally gathered, the kind of equipment that was used to analyze them was nowhere near as good as the kind of equipment that's available to researchers now. So absolutely, you will find that all three types are used, as well as pottery dating. Pottery, it's amazing how much archaeologists still really depend on the styles of pottery for dating a particular site. One that I didn't really mention, the archaeomagnetism type dating mechanism is fascinating because it actually dates ceramics and stones that have been fired, and they can analyze them for the dates where the most recent human activity took place, for example, at hearths. So that's a type of dating that shows a lot of promise for future in working with Neolithic sites.
Okay.
Okay, thank you.
Thanks so much, Janet, and we do look forward to that second part, which I've got you penciled in for April. All right, so we're going to circle back to Al. My spies tell me that that he's in the building now for the 10-minute astronomy news.
Your spies are correct. This is the 10 minutes late astronomy news. Okay, so I've got a couple news items to discuss. First one is about gravitational mergers. Now we heard some news last year about a few really cool discoveries with the laser gravitational interferometers on detecting merging black holes and neutron stars. So around 5 billion years ago, in a galaxy far, far away, two huge black holes weighing in at 34 and 51 solar masses respectively collapsed and merged into an 80 solar mass monster. The dramatic event unleashed the energy equivalent of 5 solar masses in the form of purely gravitational waves, propagating through space at the speed of light. On July 29th, 2017, these tiny ripples in space-time reached Earth, where they were detected by the most precise measuring devices ever built by humans. During its first two observing runs in 2015 and 2017, the LIGO Observatory spotted 7 merger events, 2 of which were also felt by the European Virgo instrument during 3.5 weeks in August 2017, when that instrument was operating in parallel. They've now thoroughly reanalyzed the data and come up with a few more likely events from the data, bringing the total to 11. These graphs here show you the masses of the detected events. So this is solar masses up here. These are the known masses of black holes and neutron stars, and there was one double neutron star event and another group of black hole pairs of different masses that were detected. Apart from the 4 statistically significant finds, they've also announced a list of 14 marginal candidate events that, although they're not statistically significant, may have been detections. And in February, that's this month, all of the data will actually be publicly released for others to look through it. So the interesting thing about this is this data provides knowledge of the rate of these events and in the local universe. Something like, I don't have the numbers, but they know based on this data roughly how many they should expect. And now that they're increasing the sensitivity of these detectors, and they're supposed to be coming online for a new simultaneous observing run in mid-March of this year. With the improved sensitivity, scientists expect to be detecting a new event at least once a week. So this is really cool. They're going to be an entirely new mode of astronomy available to look for things that we didn't think we could ever see. Black holes in distant galaxies, billions of light years away. So really cool stuff. The next thing I want to show you is New Horizons. New Horizons spacecraft continues to amaze. After its, you may have remembered its successful Pluto flyby a while back, controllers used the remaining fuel to redirect it toward a 31-kilometer-long Kuiper Belt object spotted by astronomers with Earth-based telescopes at magnitude 26.8, close to the outward trajectory of the spacecraft after it had gone by Pluto. In an amazing navigational feat, NASA's New Horizons spacecraft flew past this object named 2014 MU-69, more commonly known as Ultima Thule, at a range of just over 3,400 kilometers, choreographed by controllers 6.4 billion kilometers away on Earth. And that would be an angular separation of about 0.1 arc seconds from Earth. So the accuracy of the observations necessary to choreograph this feat are astounding. This particular movie shows the propeller-like rotation of the object in the 9 hours between 3 p.m. on December 31st and midnight on January 1st, as seen by the long-range reconnaissance imager, closing at 14.6 kilometers per second. During this deep space photo shoot, part of the farthest planetary flyby in history, the range decreased from 500,000 kilometers, farther than the distance between Earth and the Moon, to just under 28,000 kilometers, or within the range of our geosynchronous orbiting satellites in 9 hours. So you're moving pretty fast. And amazingly enough, they didn't hit it. They just went close by, which was good. And this is the latest image that was released from the spacecraft, from its multicolor visible image camera. The camera snapped this shot when it was only 6,700 kilometers from the object, or 7 minutes before its closest approach. This image has about 135 meters of resolution per pixel, and you can see it's a double object. There's two objects that have congealed into one here. Over the next month, the spacecraft will be continuing to send back data at a relatively low rate, but we should be getting better color and better resolution images closer to the closest approach to help unravel the mysteries of this distant piece of ice. So, very interesting stuff. Thank you for your attention.
Thanks, Al. All right, so that concludes the first half of the meeting. All right, and welcome back. I'm going to wait for Chris to turn the lights off, maybe. There we go. So up next, we've got Jesse Rogerson. He's going to give us a talk on Oumuamua. I believe that's the correct pronunciation, but I'm sure Jesse will set us straight on that. Jesse was last up last year sometime, and he gave a talk on the Cassini spacecraft, and it was quite a good talk. So looking forward to this one as well. Jesse.
Thank you. Is this thing working? It is working. Great. Okay. So, I'm Jesse. As you know, I work here, science advisor, and I really love what you do. So, before I start and get into this, I just want to say I love having the partnership with RASC. We have a good mutual relationship. We get to support what each other do. Thanks for being here. Thanks for participating in our events, and a special thank you for those that volunteered to go out on the lunar eclipse. Even though we didn't do it, you did say you would, and it was super, super nasty outside. Not as bad as I thought the sky would be, but the sky was bad. It was the temperature that was really bad. But I think we made the right choice on calling that one. That was a group decision, but thanks anyway. Hopefully we catch the next one. Was it like a year and a half from now or something like that, unfortunately? Okay, so I love talking about space, and I'm an expert in only one thing, and that's active galactic nuclei, and I think that's what I talked about last time I was here. So everything else I'm going to talk about, I'm not an expert in. Anytime I come back here, I'm not an expert in that topic, unless I repeat the talk I gave to you. So this is an exercise in me wanting to learn about things. So this is a topic I'm sure all of you know varying amount of degrees of facts about this. But I personally really only knew the headlines. I had done a couple of media hits on it based on the basic facts of the story, but I didn't really feel like I knew enough about it. So I suggested to Oscar that why don't I give a talk on this, and it forces me to dig into some of the papers and really see what's going on. So I want to give that sort of disclaimer that I am not an expert in this, and I actually was a little underwhelmed with how much we knew with all the work that's been done on it. But I'll get to it. I'll get to all that stuff. I call it the first interstellar visitor. We know it goes by lots of names nowadays. This is definitely an artist's impression of the object, and I'll get to all of that. So without further ado, let's dive in. Now, the story of the first interstellar visitor, Oumuamua, the first asteroid to visit from outside the solar system, all that. We'll get to all of that. I really want to frame it around the idea of survey astronomy. Survey astronomy is very different from your classic point-and-shoot style astronomy, where an astronomer would pick a target, go to the target, do the observation with a very specific conclusion in mind, and analyze the data. We're all very aware of this and how this works. Survey astronomy is the exact opposite. There's no intent in mind. It's let's just look at the entire sky and see what we get out of it. And both are equally useful, but survey astronomy can do some really great things. And it supported my PhD. My PhD was based on the Sloan Digital Sky Survey and follow-up observations that I did afterwards. But the backbone of my PhD, and literally hundreds of other people's PhDs, was the Sloan Digital Sky Survey. So I have an affinity for survey telescopes. And that's the story of Oumuamua, the interstellar asteroid. It was with Pan-STARRS, which I'm sure some of you know about, but I'm going to frame it around this. The Panoramic Survey Telescope and Rapid Response System, just a big jumble of words. But basically, it's a medium-ish, I wouldn't even know if I would classify it as a medium-sized telescope. It's pretty small. It's only 1.8 meters. Its first flight was 2006, and it had a sort of slow start, and then they got into survey work a little bit after that. It's got a big, huge field of view, 3.2 degrees, so that's massive on the sky. But the best part about it is that it has one of the biggest cameras on the planet, 1.4 billion pixels. So that's insane, right? In compared to your phone or your digital camera, the megapixels are like dwarfed by this. It's an order of magnitude bigger. So this is an image that's on the top of Haleakala. So I got a nice Google shot for you here. So it's not on the Big Island. It's on Maui. It's a dead volcano called Haleakala. And there's the PS1, the Pan-STARRS telescope, is sitting right up top there. And there's a second one now, the PS2, although I don't know how active it is. And there were plans for a PS3 and 4 to be on Mauna Kea, which is right about there or so. But I think those plans have fallen through. So PS1 and PS2, the two telescopes of Pan-STARRS. It's a great place. It's not as good as Mauna Kea, but it's out in the middle of nowhere, and it's a really great place to be. Now, survey astronomy has the entire point of Pan-STARRS started out with this basic idea. Let's survey the entire observable sky once every 10 days. So from Maui, anything below minus 30 dec, so this is if this is the sky, you got minus 30 dec right over there, this line, that would be cut off by the horizon, just not observable, but everything else above that would be where they're aiming for. And they just want to basically cover the whole sky with no intent in mind, really. Just let's get image after image after image after image, and we'll get lots of stuff out of that. So to give you a sense of how this works, that would be each night covering about this much. It's about 1,000 square degrees per night. That's not visible down there, and so you would do that in one night, and then move on the next night, go on to another section that big. The way it works, though, is it's not one image of that section, it's 4 images of that section per night. And those 4 images are separated by about an hour. So you have 4 images of the same spot on the sky with a cadence of about an hour between all 4, so like one every 20-ish minutes or 15-ish minutes or something like that. And what that allows you to do is quite simply see if anything's moving. And so by surveying the sky in this manner, 4 images of 1,000 square degrees each per night, you can say what's moving. And the primary funding group for this is the Near Earth Observing Program from NASA, and they're wanting to know where all the asteroids are that we don't know about. So it says, what did I say? It was every 10 days, observe the whole sky. It ended up not working out that way. It's capable of doing that, but with weather, instrumentation, the moon, other issues, it ended up being when they did the full survey, it was, what was it, 2014 to 2017, I think, was where they really were attacking it. They got 12 times, they imaged the whole sky 12 times in 3 years, so much less than they expected, than the telescope is capable of, but they still got some really good data out of it. Okay, so 4 images, same spot of the sky, you go looking, and this is what they found. 248,000 asteroids that we didn't know about. Near-Earth asteroids. That's insane. So the galactic plane is the blue line that's going here, so it's harder to find asteroids through there. They might even, I think they've actually even avoided imaging there more often than other places. And the colors of the dots represent the filter they used. So blue filter, green filter, infrared filter, that kind of stuff. So yeah, did a good job. These are the ones that are hazardous. Does that make you feel comfortable? So that's a lot. I don't know, it's kind of scary. They're within 0.05 AU of, their minimum close approach to us will be 0.05 AU. That's about 7 million kilometers. So that's, in astronomical terms, pretty close. And they're listed as potentially hazardous and ones we should follow. But it's not just locating the asteroids that it did. It created this massive catalog. So it cataloged, after those 12 hits, imaged the whole sky 12 times over 3 years. You have this is a full image stitched together, 500,000 images of about 45 seconds in depth, in exposure time. And you set a whole bunch of pipeline and software on it that picks out all the sources, like the stars, the asteroids, the comets, the galaxies, the globular clusters, the whatever, and you spend years and years and years, and you get a whole big, huge catalog that can help you do pretty much any science you want. And the list of science that you get out of something like this all-sky image is solar system, low-mass stars like brown dwarfs, young stellar objects, exoplanets, Milky Way stuff, Milky Way structure, local group of, including Andromeda and the other smaller stuff, massive stars, supernovas, cosmology. You can look at large-scale structure with this, and even close to my own heart, they found 2 or 3 really high redshift quasars in their data, unknown before, something high redshift. For those that are interested, like around 6. So super high redshift stuff. The point being is that survey astronomy does wonders, and that data is going to be useful for like lots and lots of grad students and professors. So, and publicly available if you're interested in crunching some data. Okay, so let's dive into what I really wanted to learn about, and that is that object. So this is the discovery image of Oumuamua. Now what we're looking at here is, so first of all, these red lines are masking out bad pixels, probably chip gaps, I would bet, because it's a 1.4 billion pixel camera, but it's not all one chip. It's multiple chips, and there's gaps, which is a fun thing to work around when you're doing point and shoot astronomy. You got to make sure your gaps don't land on the object you're trying to observe. So looking at the image, you have this in the red circle there, this elongated object, and that was flagged by a Canadian, Robert Verk, a Canadian working on the team, and said, oh, there's probably a comet. It got labeled automatically as Comet 2017 U1. U is the time of year in 2017. They break it down by letter. So early in the year would be close to A, and later in the year would be closer to Z. So this is October. And 1 means it was the first object found in the U time frame. Make sense? Just to give you a sense of things, these are stars here. And what I want to point out here is that you're tracking the stars, right? So your telescope is following the sky, tracking the sky motion, the star motion. And you're looking for things like this that are not circles, which means they're moving against the sky. And I want you not to think that what you've imaged there is that cigar-shaped thing from the first slide, because you haven't. It's a point source that's moving. So it drags across the image, and it gives you light in lots of pixels because it's moving with respect to your telescope. So you're not getting a shape, you're just getting something that's moving. And so they say, we found something that's moving. It's one of those near-Earth things, or one of those some things we need to find. Let's follow up on this. They looked back in the data. So this was October 19th of 2017. And they looked back a couple nights, and they found some more pictures of it October 18th, the day before. And definitely, with all of that data, you can construct an orbit and see where it's going. And they realized it's going super, super, super fast. Way too fast to be bound to the sun. And that's where the whole flurry went. Basically, a bunch of astronomers started yelling and screaming how awesome this is. So they called up all their astronomer friends, and they said, hey, every telescope in the world, can you please look at this, because it looks amazing. So CFHT, just an island over on Mauna Kea, said, yeah, we'll take a look at it for sure. So they got some discretionary time from the people from the director, and they went to where it's supposed to be, moving 6 degrees a day across the sky. So this is really, really fast across the sky. Projected by the orbit, they went and found it. Now, there's the object. It's the thing there. So this time it's a circle, and the stars are elongated. And that's because they decided to track the object, not the stars. So the stars get elongated, and you get the point source of this C2017 U1. And the first thing that they noticed about it was that there is no tail. They expected it to be a comet. That's what the C stands for. But it's not a comet. There's no outgassing. It should have had a tail for how close it was to the sun. And so they're like, oh, sorry, it's an asteroid. A2017 U1. No cometary tail, probably not a comet. Makes sense. They do know, though, that it is on a hyperbolic orbit, meaning based on all the images they'd taken, this was October 22nd, so just a few days later, all the images they took, they said this is definitely not bound to the sun. They expected, because of that, for it to be a comet, because comets live at the edges of solar systems and are easy to get lost. Meaning, if it came from another solar system, it would have been at the edge of the solar system and got kicked out easily. So they expected it to be a comet. But it turns out it's an asteroid. So that's the first few days. Super exciting. There was like 14 other telescopes that looked at it, and they started crunching things. So the first thing they did was figure out the orbit, right? That's what I've been alluding to, and it's good that I now actually have a picture for you. So when it was observed, there's a few things that immediately jump out to you that it's not from the solar system, and one is the speed. and 2 is its angle of approach. So it was actually seen after it had passed the sun. So this is where it was seen, the location of the object on the 19th of October. It had already passed Earth. It had already passed the inner planets and gone by the sun, and it was heading out. And so you, based on all the locations you have, you project the orbit. You can attempt to fit a circle to it. You can attempt to fit an ellipse to it. You can attempt to fit a parabola to it. But a hyperbola is the only thing that fits with the images that we had. And so you construct this. And you can see clearly this is coming from a direction that would be unlikely to be solar system based. So the angle and the velocity are the key. It's going at, what's the speed? Okay, this is the cool part. So it had a coasting speed of about 25 kilometers per second. It's pretty decent. It got up to 90 kilometers per second right here, and it's going to have a coasting speed of about the same on the way out. So it picked up a lot going through. Just a couple of reference points. So January 2019, it is now passing Saturn's orbit. So just now it's past Saturn's orbit. Yeah, okay. And this gives you a sense of what probably happened, roughly speaking. You have a nice whip around, and off it goes, never to be seen again. Goodbye, 2017, you won. We'll never see you again. So the funny thing about it, based on just a few pieces of parameters, you can say this is definitely not from our solar system. It's weird that it's an asteroid. Because, as I said, in a solar system, you have all the asteroids are closer in and are harder to kick out. So the hypothesis is here that this object was once part of another solar system, was somehow kicked out of it, floated through the galaxy for a while, and potentially for hundreds of millions of years, and then just happened to have a chance encounter with the sun and us. It's weird that it's an asteroid, but not completely unlikely. We just would have expected to see more comets because they live at the edge of solar systems, easier to get lost because the gravity out there is less bounding them to their star. The next thing they did is track it. So they didn't just take images of it, they just kept looking at it for a very long time. So this is magnitude, so this is how bright it is, 20-second magnitude, and this is time along the bottom here. So they were just tracking it through time. They kept watching it over and over again, measuring the brightness of it, the magnitude of it. The colors you see are the filters. We'll get to it over here, GRI, green, red, infrared, that kind of stuff. And what you're seeing is just a light curve of the brightness of the object, and it's going up and down, somewhere between 10 and 15 times change in brightness. So it's getting 15 times dimmer on a period of about 7.5 hours. That's weird, but we actually know that. We've seen this before. And we can, oh, there's more of it. It keeps going. Bounce, bounce, bounce. It's a weird, like, half circle. But we actually recognize it very well. And it is actually because of something like this. So this is a simulation. You could write a computer code that takes an elongated object, tumbles it end over end, and if you look at it, you'll see a long face and then a short face, and then a long face and then a short face. And because of that, there'll be more reflection, less reflection, more reflection, less reflection from the sun, and you get this bouncy curve. And that's why we think it's elongated. We don't know it's elongated. It could be a sphere that has one side completely white, meaning super highly reflective, and one side completely not reflective, and be spinning. And there's some precedent to that because there's a moon. What's the moon that's like that? Yes, see, you guys know. Now, that is a possibility, but because of where this has come from, that moon, was it Iapetus? That moon likely is that way because of the place that it is, that there's something has made that side a different color, whereas this has been floating through the universe for a while. It probably is the same color all over. It's likely, the most likely scenario here is that it's a tumbling thing that's about 10 to 1, 10 times longer than it is wider. So artists get together and they make this cool image. Yeah. Or video. Yay. It's weird looking. So this is the image I started with. This is an artist's impression of A 2017 U1. It does have, it harkens to, what's the name of that thing from that science fiction, Rama, yeah. It kind of feels like Rama a little bit. Although I don't know if I don't know much about that science fiction story, but I don't think it's tumbling end over end in it. Yeah, okay. So it's anywhere from about 100 to 1,000 meters. We don't really know. It depends on what you assume the reflectivity of the object is. If it's really dark, it'll be a different size than if it's really bright in its reflection. And they changed the category. They decided that comet and asteroid don't fit this. This is the first object in an interstellar category. So it's now I 2017 U1. But then, yeah, right, it's cool. So, but then it's the first interstellar object that we've seen. So a bunch of cool people got together and said, maybe we should give it a real name, like its own name, the way we name things in our solar system. And so one of the main groups that is running the Pan-STARRS survey is the Institute for Astronomy at Haleakala. And at that Institute for Astronomy, the University of Hawaii, they went and found some language experts, some Hawaiian language experts. And they are Kayu Kimura and Larry Kimura. And they thought about the origins of the object and decided that it should be called Oumuamua. This is, I forget the name of this. I looked it up before as well. This is a little accent that's kind of like a quick pause. And in Hawaii, I don't speak Hawaiian, so if someone here has a better experience and better understanding than me, I'm sorry. But I'm pretty sure, from what I've read, you have to pronounce each letter exactly as it sounds. So this would be Oumuamua. Oumuamua. And this O is a reach out for, quote unquote, and the muamua places an emphasis on first, so first or in advance of. And it kind of makes sense. Now, I've heard this rephrased in a whole bunch of articles to be visiting a scout from afar or scout or messenger from our distant past. But this is straight from the Institute for Astronomy in Haleakala, so that's the best translation you're going to get, which is pretty cool. Oumuamua. Oumuamua, if I say that right. Now, the next time we find an interstellar object, it won't get a name. It'll be called I 20-something, whatever. It won't give its name. But this one's cool, so it's the first one. Okay, so I'm sure you're all asking this question. And there's your answer. So where did it come from? We have no idea. Absolutely no idea. We do know that if you trace that hyperbolic orbit backwards, it points at that spot on the sky, which is about 5 degrees away from Vega. However, for it to get to Vega at the speed, its cruising speed, it would take a very long time, hundreds of thousands of years, 300,000 years. And Vega probably wasn't there, or wasn't as close as it is as we think it is right now. So we have to be careful. We can say the direction that it came from, but the Milky Way is rather chaotic, and knowing exactly where all the stars were at all the points in history is a tough thing to do. I have read one paper that did attempt to do that. And they had 4 possibilities. They were all small brown dwarfs, or there's a brown dwarf, a white dwarf, and some M dwarfs in the direction that could be possible homes, but they said it wasn't a strong correlation, which is why I didn't put them up. And none of them are known to have exoplanets, which would have been cool. But none of them have exoplanets. So that's where it came from. Where's it going? Pegasus. So it's heading out to Pegasus right now at that exact point. So you can go point your telescopes at it, but you won't see it. Can we visit it? No. I'm pretty sure no. Unless you invent some crazy kind of, perhaps if we made a concerted effort, we might be able to catch up to it, but I think we've kind of lost our chance. Perhaps if we saw it coming in, we might be able to match a velocity, but that would take some serious planning. Okay, so I'm going to dive into 2 surprising conclusions / observations about this. What was my first one? I forget. Oh yeah, this one. Okay. Non-gravitational acceleration has happened. So maybe I should back up on this. Non-gravitational acceleration. So before we watch that. So it's supposed to be free floating. It's floating through the universe, floating through our Milky Way. It happens to have a chance encounter with the sun, but that chance encounter is just a gravitational blip. So it feels the sun, it falls towards it, it speeds up, it goes around it, and it starts flying out. It should act like a ballistic object, meaning the only thing that we're aware of that's acting on it is the sun. So because we understand gravity on that scale really, really well, we should be able to predict exactly where it's going to be at its next time frame, whatever time frame you want to say. Next second, next hour, next 2 days, next 3 days. You can predict it because we know how gravity works. So we do that. We say, here's where it should be. And then we keep watching it for as long as we can. And we notice something weird, and that it was not in the spot that we thought it was going to be. It had this expected trajectory. It actually ended up being at this observed trajectory. That was January 2nd there. And, oh, that's from NASA. And I think I have, here we go, this is a little better. So it had this sort of, the two numbers are different, slightly different, but they had this difference in distance, a difference in location that didn't match our gravity. Now, our understanding of gravity at this scale is really, really good. So on galactic scale, we might be a little off, or on intergalactic scale, we might be a little off, but we know how gravity works in our solar system. And so we're not wrong about that, which means something else has acted on it. The best way to say it is, it is slowing down, but it's not slowing down as much as we thought it would as the sun tugs on it. So what is this? Why? This is one of the surprising results. And then a bunch of people started saying some interesting things. So possibly the sun is pushing it. This is called radiation pressure. A couple of researchers from Harvard Institute for Astronomy, or Center for Astronomy, Avi Loeb was one of them, who's a very outspoken science communicator and a really, really cool person. But he and another person wrote a paper that speculated, and a non-peer-reviewed paper, by the way, that speculated, what if the sun was pushing it? Okay, we understand that the sun can push. Photons have momentum. They can impart momentum. They can perhaps push on things. We use that exact idea to stabilize the Kepler Space Telescope for its final years. So looking into that, in order to create the amount of push you need to create the expected difference in the orbit, it would, instead of it being a cigar shape, it would have to be a pancake shape. And then Avi Loeb and the other person from Harvard, who I don't know the name of, said, if it's a pancake shape, maybe it's a solar sail. And therefore, it's an alien spaceship. So you may have heard of that in the news, which I'm not going to say is not worth looking into, but there's some serious problems with that. So the first is, what about the brightness? So if it is a solar sail, why is it changing its brightness? Why would unless the solar sail is tumbling for some reason, but then it wouldn't act like a sail the right way. So that's a huge hole in that argument. But the real interesting one, so if you're suggesting that it's a solar sail and that the reason it's changed its motion, the non-gravitational acceleration, is because it's a sail, then it would have been made by some intelligent species. And if it's an intelligent species, then you think it would have been on a better orbit. It would have, the 25 kilometers per second that it's now leaving the solar system with, and slightly more because it's getting pushed by the sun, if it is a solar sail, that's not going to get you anywhere fast, anywhere. The point of a solar sail is to make them super big and make them go super fast, pick up lots of velocity on really, really long timescales. This is not a big enough. The sail that it would have to be is, I forgot to mention, would be about 30 meters wide. You need an order of magnitude bigger than that to make any real dent at the distances in the universe. So it would be odd for an alien race to create such an inefficient solar sail. So, not to mention, it makes the brightness is really indicative of a tumbling cigar-shaped thing. So if you have read about this, it's worth asking the question, but I sincerely doubt that it is that kind of ship. Sorry, everybody. So what is the effect? What is making that motion? It's probably outgassing. It's probably some small amount of volatiles on the surface that have outgassed and have imparted some velocity to it, almost like you letting a balloon go. It had gas locked up inside as ice, and it got sublimated. It became a gas, and it shot out the back of the object, and it imparted a little bit of velocity to it. And that's probably the most likely thing. Now, I go back to the beginning, and I say we saw no outgassing, even at the close approach to the sun. And there's two things to say about that. One, when we saw it, it was what was it? The CFHT images. It was way past its closest approach, and it was I think it was like 0.4. Oh, I can't remember. It was pretty far from us, and it was much farther past its closest approach. So maybe the outgassing wasn't as strong as it could have been. CFHT has a really good camera, so it should have seen it. However, what cometary tails are most bright when it's very dusty. Maybe there wasn't a lot of dust in the tail. Maybe it was just gas that was let go. That could be one solution to it. The other thing is that we're used to looking at comets that are in our solar system, and we know how they act. When you have something that is flying through the Milky Way for hundreds of millions of years, it's been impacted by cosmic radiation for all of that time, really affects the surface and might lock the dust down and the gas down much, much stronger than it would in our own solar system, which are protected in a way from that kind of radiation. And so its flyby of the sun just didn't let go as much gas and dust that we would have expected from a comet from our solar system. So maybe it is a comet, after all. We don't know, but I think it's a comet. Now I'm going to leave it with this. Yep, I'm going to leave it with this. So this is the thing that I really like, and I want to wrap it up this way. Because I was trying to look at it through the frame of survey astronomy, right? So these are two quotes from two papers that I read, and the first one says, at any one time there are 10,000 interstellar bodies of U1 size, so of Oumuamua size, from Neptune in towards the sun. What? 10,000? Where are they all? This paper said, interior to Earth's orbit, there's at least one all the time. So this is the really interesting conclusion about Oumuamua, is that they are here. They're flying through the solar system all the time. Interstellar objects, stuff flying from throughout the Milky Way and making chance encounters with our solar system and going on their merry way. Survey astronomy is what makes it possible to see these. Unless you get one that was really close to the sun, like Oumuamua, it's not going to be bright enough to catch on any regular basis. You need a survey astronomy that's constantly looking. Oumuamua was even though the Oumuamua was close to the sun and as bright as it could be for us, it took pan-stars to see it, and pan-stars wouldn't be able to see it if it flew through at Earth's orbit or not Earth's orbit, past Saturn's orbit or further. So the ones that are like Saturn and out, we just can't see. We're not surveying fast enough or enough of the sky to catch them. So because we have pan-stars, because we're surveying all the time, we picked up this one. And that's a really good thing, which makes me really excited about the next generation. And I meant to put a picture of it, but there's two telescopes that are being built, one particularly that's really important called the the LSST, the Large Something Synoptic Telescope. I forget what the other S stands for. Thank you. Survey, of course. Large Survey Synoptic Telescope that's being built by the United States, and it will do an even better job than pan-stars. It's going to be an insane amount of data coming from that telescope. It's the flagship mission, the flagship project of the United States for the last 10 years. And it will catch more of these. So they are there. Oumuamua is just the first. It's literally the scout in first in advance of a whole area of astronomy and astrophysics, or planetary science, I guess we could say, that is just beginning. Think of this like exoplanets in the late 90s. It's a whole new field that's just getting started because we know how to look now. And that's where I'll leave it.
All right,
Yeah,
so we've got time for a couple questions.
Keeping in mind, I'm not an expert.
No, I know that. My question to you is, you mentioned the particular equipment that you use for this survey astronomy.
Yes.
You can capture 4 similar scenes per day?
So that thousand degrees that they catch per night
Yes.
is imaged 4 times.
Okay, my
Yeah.
question to you then is, having that capacity, can you establish a stereo pair and see objects 3-dimensionally instead of 2-dimensionally?
I would say no, because it depends on the target and how close it is, I guess. Because like all of those asteroids are point sources, so you're not resolving them enough to get a 3-dimensional view.
So we're just seeing them in 2 dimensions.
Yeah, I suppose 2 dimensions. It would need to be a lot closer to Earth, from what I understand, for it to be resolved as an object.
Okay, thank you. Yes?
He was louder than me.
1.5 billion pixels. How many terabytes of data are we?
Oh, I looked that.
Data are we?
I think I looked that up, but I can't remember what it is. It's a stupid number.
We're not going to be able to play with it on our PCs.
So you're not going to be able to play with all of the data at once, but if you are interested in like specific things, you can query it. The data is available to you, but it's also like you need to know what you want, and you need to use they have SQL. It's a SQL database, so there's like a lot of tutorials you need to go through before you can start being good at using it, which is why only grad students and professors use it. But it is available to you. There's like terabytes and terabytes of the Sloan Digital Sky Survey, but I could download images of quasars onto my little laptop hundreds at a time. So, you can take small chunks of it.
All right, just 2 more.
Yeah.
Based on the projected orbital path, it looked like it came relatively close to the Earth, or at least our orbit.
I think the closest was 0.25 AU. It wasn't that close. Yeah, it was okay.
All right, last one.
Up the back?
Yep.
What do you had infrared data? Was it far enough into the infrared to get temperature measurements to find out the density or the material properties?
They got color, so they know that it's red, and then they put Spitzer on it, and they didn't see anything. It was too far away. So that doesn't answer your question. I'm not 100% certain on properties of like material. I think they're making assumptions based on reflectivity. So I'm not 100% sure. It's probably the best answer.
So that's how they got the size of the thermal.
The size comes from the tumbling and the reflectivity. And so it's not. I wouldn't say it's thermally related. It's color related, which I guess is kind of thermal.
All right, thanks, Jesse. If there are any further questions, maybe Jesse will field a couple of those after the meeting.
Yeah, I'll be around.
Great. Thanks, Jesse. All right, up next, we've got our observation reports. So if you're on this list here, if you could just queue up along the side of the podium there.
So can I line up, Oscar, and give a null report? What's that have to do?
So you can just advance the slide there for yourself. Very good.
So this is a 20-second exposure of M33, the Triangulum galaxy, which I got from using the Malenham exterminator. Oh, thank you. the Melancam exterminator, does this work? The Melancam, I'll speak loud. The Melancam exterminator connected to a Celestron 8-inch Smith Cassegrain. M33 is the third largest member of our local group, behind the Milky Way galaxy and the Andromeda galaxy. It's approximately 3 million light years from Earth, slightly more distant than M31. And some of the, most of the H2 regions which are associated with star formation are located in the central part and also along the spiral arms of the galaxy. My next endeavor is to get a wide-angle shot of M33 properly centered in the frame. Thank you.
All right. Thanks, Jim. Up next is David.
I happened to be in Phoenix for the lunar eclipse. And because I knew that I was going to be there, I did take some equipment to take pictures. And so I did capture it, although I was disappointed because it was hazy there. I was there 6 days, hazy the first night on Sunday night and clear the rest of the nights. But I did manage to get capture. I took about 450 shots and started about 9:30, I think is when it started in Phoenix, 2 hours earlier. And I was using a Canon 20DA with a Skywatcher tracking mount. So this is what I captured. What do I hit here, Oscar?
Just hit the right button.
And by the way, the last picture was shortly after, when you see it finish. There we go. When you see it finish, the last picture cleared up right at the end after it was over. So you'll see. But you can see that there was haze. And I cut out, there was a lot of shots that got blocked completely with clouds, so I just took those all out. And I found the biggest challenge, I've only done one other lunar eclipse, was finding the right speeds, so changing the speeds as the moon got brighter. And that was after, like 10 minutes after it was done. Thank you.
Thanks, David. All right, up next, Gordon.
So what are we doing here?
You can hit the button on the right to advance the slide.
Button to
Yep.
advance. Okay. So I've tried to go out a few times over the past couple months observing. And as you've probably noticed, it's either really, really, really cold and clear, or it's really, really cold and cloudy. So on a couple of really clear nights, I've set up my telescope in the backyard to cool down, gone in, had supper, and come out, and I'm not sure what I'm seeing. So I figured I might be able to do a better job seeing it in the daylight. So this is a painting done with colored pencils, and it's about a 10-hour exposure. Now this was the lunar eclipse. Unfortunately, this isn't my image. This is one I stole off of Astronomy Picture of the Day. However, we in Ottawa got something that this photographer did not. We got an eclipse of the eclipse. And there you go. And if you look really closely, is this right there, you can just see the faint crescent. This was done just a few minutes before the total eclipse. There you go. So that's all I have for you. Thanks.
Thank you, Gordon. All right, up next we've got Pierre Martin. advance the slide there.
All right. Well, good evening. So I went out a handful of times in December for meteor observing. First couple of times in early December, it was super frustrating because the weather was supposed to be clear, and I drove out to dark sky side only to be frustrated by completely overcast skies. But finally, on the evening of December 12th, just one night prior to the peak of the Geminid meteor shower, was looking very promising. So a good friend, Raymond Dubois, and I, we decided to get together, pack our gear, and drive north of the city where the prospects looked best for clear skies. So this was on December 12th to 13th. So there's the location. We drove up there. We found a nice quiet spot on the edge of a frozen lake. And it was really interesting because we had a beautiful view of the southern sky. It was really dark as well. So we set up our gear and we watched for the entire night. And the sky was crystal clear. The Geminids were very active that night. I saw on average between 40 to 50 an hour, which is pretty good for the night before the peak. And this had also my two cameras running, my two digital SLRs. One running with a wide-angle lens and a 24 millimeter, and the other one had a telephoto, had my 70 to 200 that I had set to about 135 to do some close-ups, as I'll show you. So this was a wide view over the lake, and it's a composite image. So it's basically, I did a series of short 1-minute exposures throughout the entire night, right up until we finished at about 6 in the morning. And then I stacked the pictures with meteors on that field of view. I stacked those in place, and this one had a good handful. So the meteors on that pre-peak night were actually relatively faint. It was a pretty active night, but very few fireballs. The brighter meteors for the Geminids seem to occur more during the peak, and then after the peak, you get even brighter meteors. Although the only downside of that night, it was really, really cold. It reached a low of minus 26. And if you don't believe me, ask Raymond. He'll tell you how cold it was. We were really frozen at the end. So we were like with our parkas and all our gear and our heaters and everything, but it was still very, very cold, very humid. That kind of cold that comes right into you. So a few more results. This is Comet. This is 46P Wirtanen. And I had the camera with the telephoto lens aim into that direction. And some of the Geminids appeared in this location. This is a composite as well. So I was quite lucky to get that bright one just passing almost right on top of the comet. And Wirtanen was actually visible naked eye, just barely from that dark sky side. You could kind of see there was like a very faint patch in the sky. Through binoculars, 9x63 binoculars, it was actually quite obvious to see. There's another part of the sky I imaged. This is the M44 Beehives cluster with Gemini scooting by. And that was a shot of Orion setting. So close up on Orion, and you can see there's a faint Geminid on the bottom left. And that's the result of the Geminids. I'll just switch it back for now. So that was the first night of observing. Unfortunately, the peak night, the following night, it was completely washed out. We would have had to travel down to a place like Texas, and that was not going to happen this year. With the moonlight interfering a little bit in the shower, I decided to try to observe the Geminids locally. So it's unfortunate because it was a very strong peak. From the IMO side, they reported that the zenith hourly rate reached well above 120. Went to 120 and 130, which is the typical average high for the Geminids. So that was the last big shower of 2018, and then I decided I really wanted to try to see the quadrantids, the first big shower for this year, which peaked on the morning of January the 4th. If you recall, on January 3rd, there was an evening, it was a lot of snow squalls, and it was cold, it was windy, there was like a lot of bad accidents on the highway. I decided to take a chance and take a drive out at 2:30 in the morning. It was like I could see there was a cold front coming through from the southwest. And I figured, okay, I'm going to give it a try. It's new moon. It's ideal. You know, what the heck? It's a weekend. Might as well just see what happens. So I drove 2 hours out towards the past Caladar along Highway 7. And then eventually the roads got better and it was easier driving. And I got to the Lennox and Eddington dark sky site. That's the place along Highway 41 south. And that looked like that would be the first place to clear before dawn. And I might have a shot at seeing something. So I got there and the sky started actually to clear. And I was seeing quadrantids left and right. Like it was pretty active. And even though the peak of quadrantids was several hours earlier, and it's a sharp peak, so it really doesn't last long. I was actually seeing a lot going on, so I figured, okay, I'm going to set up my chair, and I got my camera, but I'm going to wait. I'm just going to go visual, because there's only an hour and a half, maybe 2 hours at most, before sky gets bright. So the first hour, I counted, if I recall it, about 38 quadrantids, 35, 38. And then the second hour, there was only 13. So obviously, the rates were really dropping fast. But there was some beautiful meteors. And there was one fireball that I saw that was not part of the quadrantids, but it was a Coma Berenices of mag -4. It was like a lightning bolt that shot through the sky. Really, really cool. And then that was it. I observed as long as I could until the morning dawn and packed up and went back home. So no pictures to show of that shower because I just went visual. But it just goes to show sometimes you just have to give yourself a chance. If it looks like it's going to be really bad, you might actually look in. And the quadrantids is one of those showers that you really have to be the right spot. It's all about timing and also being lucky because the weather can be really tricky. And if you do get to see the peak, the actual the highest intensity of the quadrantids, you're lucky because you're going to see probably something as good as the Perseids or the Geminids. 1 meteor a minute or better. But you have to be really, really specific. A lot of people have not seen the quadrantids just because it's one of those showers that's difficult to see. But I was able to see a little bit of it. So hopefully this year we'll get some more of those showers. The moonlight's going to be challenging for some of the bigger showers this fall. But there's also minor showers in between that we can hopefully check out. Thank you.
Yeah.
Oh, question? Yes?
Okay, what you're showing me that is that cold weather doesn't affect equipment. Does that apply to telescopes as well?
You have to be really cautious with the equipment. I find the biggest challenge is when you're working with cables. In a really, really cold weather like this, everything gets really cold and brittle, and things will break easily the moment you start moving them around. I find with the cameras, as long as there's a heating source close by, and usually what I do is I have my Kendrick heaters around the lenses, that's enough heat transfer, just enough to keep the camera body warm.
But it wouldn't steam up the lenses?
Not if you run it relatively low power. I keep an eye on the lens like every once in a while during the night, and they stayed clear the whole time. And the batteries, the best thing to do when it's that cold is run external battery. You have a power pack, something that's going to give you enough juice, and then run cables to that instead of the small camera battery that's going to die in no time.
Okay, thank you.
Great,
Thank you, Pierre. I'll take the clicker from you, though. Thanks. All right. Taras.
Spoiler alert, this is not my picture. I wish I was able to take it, and it was almost to happen. Myself, Andrew Brown, Eric, we planned on going as far as Mattawa. It was like about 3-hour drive from Ottawa at some place where it would have been -27. And we thought twice, and well, we had that thing in the back thought that maybe it's not worth it, so we canceled last moment. Mostly because of the concerns that you cannot be exposed for that too much cold for that period of time, which needed to take even a time lapse. So time lapse was not on the list. Essentially, we stayed home. And what do you do then? Well, you Facebook, you talk to friends, you watch other pictures showing up in the Facebook feed, and you discuss them with friends. And one of them happened to be in Toronto, where they had amazing clear skies, and they had all the conditions which are needed, which we didn't have here. So I was still complaining to him, and coincidentally, he is a videographer. He has a video camera. So, well, give it a try. No, it's too cold. It's minus 27. Yeah, but you have the balcony. So take your camera to the balcony, which he did. And he took a few shots as a video footage. So this was about like 2 to 3 second length. And the individual frames are a bit noisy, so I asked him to upload it through Dropbox and stack them to reduce the noise. So this turned out to be pretty decent picture, showing actually a little bit of blue color because of well-known fact that when there is atmosphere, when the light goes through the atmosphere, the blue lights with more energy, that they get deflected less because they have larger amount of energy. So the blue comes first, and then the red comes last. And a few minutes later, when he took next picture, you can see the red approaching as a shadow. It's still penumbral, which means that it's a kind of semi-shadow moving this way. And well, it's overexposed in this part, but this part is showing up nicely to the craters. And the third picture, which I tried to convince him to actually do that one more time, because the lenses got moist when he got to the back in his apartment, so obviously the temperature change didn't work well for the lens. But this was taken at 11:43, which was half an hour before the totality. What's interesting, though, that 2 minutes later, after this picture was taken, there was a impact, a meteor struck somewhere right there. And it shows up on, again, if you follow the history of this eclipse, there is a number of videos which show that meteor impact as a very short, like 2 to 3 frames, video frames duration, a little bright spot hitting the surface of the moon at 11:45. So he was 2 minutes early with this picture. But I'm really happy to show this to you and share that story, because, well, this is the only what could have been distantly gotten from Ottawa as a glimpse of the eclipse. This was taken by me in 2015 when we went for a similar solar eclipse with Eric Limay. So that's Eric's scope, my scope, and the place itself is the Upper Canada Village. There is a monument. And what I like about this picture was a halo around the moon, which was actually also in penumbral state. It was almost totality. It doesn't show up because the actual moon is quite tiny, and I increased the exposure to show a little bit of the panoramic view. So of the view. When it was happening, it was really first eclipse for me. I was almost like speechless, as it gave me goosebumps back then, because I didn't see full lunar eclipse in totality. And the place was kind of too catchy to take this picture with the moon on the top. And again, the same 2015 September eclipse, where all the phases of the eclipse, I put them one by other to show all the progression of the ingress of the shadow, the full eclipse, and the shadow constantly, slowly receding. Thank you.
Thank you, Taras. Gary, you're up next.
Thank you, Oscar.
Well, the planets of our solar system have been viewed for thousands of years. The 5 naked-eye planets are Mercury, Venus, Mars, Jupiter, and Saturn. And along with the sun and the moon gives us our 7 days of the week. Well, even to today, people have been noticing the planets, especially in the morning sky. Now, I've been on 8 radio stations across Canada promoting the lunar eclipse, and about half of the interviews ended with, what are those two bright things in the morning sky? They're, of course, the brightest planets of our solar system. Here we have bright Venus and then Jupiter off to the right. And with technology, this picture was taken only 15 hours ago. It was this morning's sky. So it's great to see that people are asking questions. Even in the office, many people are asking what are those bright objects in the sky. And we tell them the planets, they stand back. You can see planets with your naked eye. So right then, you've kind of hooked them into the science of astronomy. So that was this morning, a little bit of Earthshine over here, or Da Vinci glow. Venus and Jupiter. Venus is about 52% lit. It's now it's descending every morning. It's going to round behind the sun. It'll get smaller but larger. Nice perfect circle. And I noticed when looking at this image on a computer and really zoom into the pixels, I actually imaged Ganymede just on the right. And I checked with one of the apps, and that is just a 6-second exposure. Shows you what just a simple camera can do. Have a good night.
All right, thanks, Gary. And Paul.
Thank you, sir. Well, good evening, everybody. And as I don't need to say, yeah, the eclipse was pretty challenging. I'm just curious if I can get a show of hands. How many people actually got a chance to see it, even just for a moment? Well, we got a few. Good. A few diehards. Excellent. All right.
Saw it on the internet.
Me too. So this was an eclipse that was well positioned for us, high in the sky. Totality occurred around the time of transit. You know, you're talking about elevations over 60 degrees. Everything would have been perfect, except for the fact that we had clouds in Ottawa, and the temperature was forecasted to be about minus 23, minus 25, with some rather brisk winds, 30 to 45 kilometers an hour. So that made for a bit of a chilling evening there. And so as Terrace mentioned, there was a bunch of us that were planning to head out, you know, up maybe towards Mattawa or North Bay, because that, based on the satellite imagery, it looked like that place was going to be clear, and we were going to miss it, like we did in Ottawa for the 2015 eclipse. So we were thinking of going up there, but I thought to myself, probably not one of the smartest things I would have ever done, because it would have been about a 700-kilometer round trip on highways, and I checked the data on this. The highways were either partially or fully snow-covered. And with 45-kilometer-an-hour winds blowing your vehicle around, like I said, probably not the smartest thing. So basically, I wrote off the eclipse. I thought, well, some typical Ottawa eclipse, we're not going to see it from in town. I did get lucky, though, as you can tell. So these are a few shots that I took. I basically wound up setting up my equipment at my place. So I'm about 20 kilometers west of FLO. And the sky did start to clear. It was at no time it was perfectly clear, but it did clear enough for me to grab some images. So these are some of the best shots that I was able to grab from the time that the moon was in the penumbra. You can see it, basically the progression is down that way. And you can just see the last of the lunar surface being lit by the sun there before it slipped into the umbra totally. And then just illumination as it starts to slide out of it. Totality lasted for 62 minutes. It was interesting, but I didn't expect to get anything because just 3 hours before the eclipse, this was my sky at home. Yeah, but that was actually better than I thought it would be for that time. We knew from the weather data that the front was going to pass through Ottawa. It was just a matter of timing, and I didn't actually expect it to clear my place that early. But I could see it was starting to break up, and I thought, well, maybe we'll get something. It's not going to be a night for high resolution or anything, but maybe see the eclipse and get some interesting eclipse shots. And as it turned out, just around the time of totality, it did start to clear out. And so you can see this is a shot with a 16 millimeter lens there. You can see the moon and the beehive cluster. Down here, Procyon, up here, Pollux. So it did start to clear out. I don't know if you can make it, but there's certainly still some reddish haze down at the bottom of the image there. This, again, just at around the time that totality was starting. And I think, unfortunately for folks in Ottawa, that front passed through at around the time that totality was ending. So I was lucky to get about a half an hour break on that. But I did get enough to see it. It was a really nice sight through the binoculars. And I also had a chance to set up a little closer view. So I had two cameras going, one with a 16 millimeter lens. I had originally wanted to do some higher res stuff, but that was out of the question because the sky was just junk. So I wound up just shooting with 16 millimeter and with a 300 millimeter. And so we managed to get that. You can see the moon there, and you can see the beehive cluster. And again, this composite image, because to catch the stars was a little bit more challenging than catching the moon there. You had to use shorter exposures for the moon, longer for the stars there. So we did get lucky enough to at least see it. As you can see, this is almost a full scale on the 300 millimeter. There's not a lot of detail on the lunar surface other than the mares, but not a lot of crater detail. You can see Copernicus here and a few other, you can see the rays coming off of Tycho a little bit, but certainly not the clearest night that I've ever been observing. But it struck me, it was interesting because this was the harshest night that I've ever been out observing. In all the years I've done observing, the temperature at my place hit -25 without the wind, and we're getting about gusts of about 40 kilometers an hour. So wind chill was down around -40, -45. And I thought, my God, this is, I must be crazy to be out in this. Fortunately, because I wasn't shooting this from my observatory, I was actually out in the field so I could get the clearance that I needed. Had a bit of a wind break with parts of the house there, but pretty harsh night there. But it reminded me, it wasn't the coldest night that I've ever been out. My own personal record is -30 degrees, but there was no wind. But the interesting, just a thing of personal interest and coincidence, is when that happened, because this was our eclipse of January 21st, 2019. Exactly 19 years, pretty much to the minute, before this was the night of my coldest ever observation. So 19 years prior to that, and I just so happened to be imaging an eclipse of the moon. So within a couple of minutes, 19 years later, yeah, my two kind of most challenging evenings there. This was obviously imaged with a larger instrument. This actually with a 10-inch LX200, so you can see a lot more detail. The night was perfectly clear, and there wasn't a stitch of wind. But it really got me, the timing of this, like pretty much to the minute, exactly 19 years. So when I was out shooting this, I think, was that part of the Saros cycle? For those of you, I'm not going to go into detail of that because it would take too long. But Saros cycle is a repetitive cycle of lunar and solar eclipses, if you want to Google it. And I thought, I wonder if it's the Saros. But the Saros cycle itself is about 18 years and 11 days and 8 hours, give or take. And this was exactly 19 years. So as you can see from the previous one, whoops, sorry. Part of a different Saros cycle, Saros 134. And so it wasn't the same. This is Saros cycle 124. There are numerous of these cycles, and what these cycles tell you is that an eclipse every 18 years, etc., will occur in pretty much the same place and the same time from anywhere on Earth. So wasn't part of the cycle, but it was exactly 19 years, which struck me as really odd. So anyway, the things you think of when your brain starts getting numb, you know. I don't know. Anyway, it was a wonderful night of observing. Wonderful night of observing. It will certainly be very memorable for me just because of the conditions, and maybe I'm getting smarter in my old age there and not deciding to drive up to North Bay to see this. So I was rewarded with a reasonably good view, and again, showing the progression there from the start down this way to it leaving there. So I'm glad some of you managed to get a chance to see it. Makes me feel like I'm not the only totally crazy person in the room. Thank you.
All right. Thank you, Paul. So now we're on to observing challenges. So last month we had the Orion Nebula as our beginner challenge, Able 12 as our intermediate challenge, Able Galaxy Cluster 426 as the advanced challenge, and the creators Armstrong, Aldrin, and Collins. Did anyone get out to try to bag any of these challenges this month? Too cold, too snowy? Yeah. All right, for February, our beginner challenge is going to be the Crab Nebula. So it's up in Taurus. It's a supernova remnant, 8.4 magnitude, visible in small scope, but you need a larger scope to get some of the detail. Our intermediate challenge will be the Rosette Nebula, or Caldwell 49. It contains various NGC objects there. So the clusters are easy to see in smaller scopes. But the nebulosity requires a larger instrument at low magnification and fairly dark skies. Our advanced challenge will be Sharpless 2-301, which is an emission nebula in Canis Majoris. It's approximately 9 by 8 arc minutes. It's best viewed with a large instrument, and you might need something like a UHC filter to draw it out from the background sky. Last but not least, our lunar challenge, the Alpine Valley Rill. It's located on the floor of Valles Alpes. The rill is right down the center of the valley. It's about 140 kilometers in length, but never more than about 1 kilometer wide. So it's pretty tiny. You'll need something like an instrument that'll give you about 150 times magnification to see it. All right, so to recap, M1 for beginners, Caldwell 49 for intermediate, Sharpless 2-301 for the advanced challenge, and the Alpine Valley Rill for the lunar challenge. All right, FLO star parties for our members. The next one is next Saturday, February 9th. Hopefully it's not too cold, and hopefully it'll be clear. We'll see. So stay tuned, I guess, for a go, no-go the morning of that day. Estelle's pick of the month is Journey to the Stars, so be sure to rush to the library after the meeting to check that one out. Here are some of the folks that help run the club. Thanks very much for your contributions. Our meetings are available online for viewing. Thanks, Michelle Bois, for recording them. And thank you, everyone that attended. We had 100 attendees, and thank you to all the speakers, and thanks to the museum for hosting us. Our post-meeting entertainment will be at Gracie's. That's at the corner of Ogilvie and the Aviation Parkway. So feel free to drop by for some drinks and some conversation. Our next meeting is Friday, March the 1st at 7:30 p.m. I've got a really exciting speaker lined up, Dr. Matt Kaplan, who's an astrophysicist at McGill. He's going to be giving us a talk on the inner lives of dead stars, so it's a pretty fantastic talk, not to be missed. And membership benefits, you get access to the Ted Bean Lone Library, the Stan Mott Book Library, and the Fred Lossing Observatory if you join. You also get these great publications, Sky News, the RAC Journal, the Observer's Handbook, and Astronauts as well.